Hi, my name is Muhammad Shafiq Imran, and today our team would like to present about our finite element method project analysis, which is skateboard load case. Our team member consists of Yo Wei Kang and me, myself, Muhammad Shafiq Imran, and Ling Chung Tek. So, let's go. So, maybe you are wondering why skateboard instead of other objects. First, because skateboard is an extreme sport that involves a lot of tricks. So in this analysis, we are going to study and analyze on how this trick can give impact to the skateboard structure. In this study, we are going to study based on two load case, which is load case 1, a normal skate, while the other one is a wheelie trick. So let's focus on normal skate. Normal skate, where one foot of the skater is on the skateboard, while the other foot is hanging in the air. So the weight of the skater is located at the center of the skateboard. So in this analysis, we are going to find how this load can give impact to the skateboard structure. On the other hand, we have a load case 2, which involves a wheelie trick or manual trick. This trick involves balancing on one side of wheel while keeping the other side of wheel off the ground. In this analysis, we are assuming the deck is made of balsa wood, while the wheel plate is made of aluminum alloy 7075. So, without wasting any time, I would like to invite Mr. Wekam to present the load case 1.
Hi, my name is Yo Wei Kang, and today I'm gonna present about load case 1 in our project. As in the load case 1, the situation being stimulated is when the user step on at the center of skateboard. This is very common in skateboarding. As shown in this figure, it is the real-life situation of the load case 1, where one leg is stepped on the skateboard and another one is trying to move the skateboard forward. For our stimulation, the material choose for wooden board is balsa wood, and for the bottom part, the material for wheel plate is aluminum alloy 7075T6SN. Before we start the stimulation, there's few assumption was made, which is the skateboard is moving on a flat surface and the friction between wheels and road is negligible. With this assumption, even though the skateboard is moving forward, however, the level of the skateboard is keep constant from start to the end. So we can act the region where the wooden board joining with the wheel plate is the fixture. So there's two fixtures in load case 1. Next, we assume that the user is 75 kg. The area of footprint is simplified into a simple rectangular shape and assume that the body weight is uniformly distributed on area of footprint. So in the next slide, I will present about the result of the simulation. So in this figure, it shows the result of simulation of von Mises stress. The blue color represents the region where exists the lower stress, and when the color is being lighter, it means that the stress is increased. So at upper part of skateboard, the higher stress exists at center of the skateboard, which is also the region where the user step on. The another region where exists the higher stress is at the upper part of skateboard, where the wooden board is contact with wheel plate at bottom. So we can see at two regions here. However, this is not the highest stresses occur on the skateboard. but we can see in this figure which show the critical lock region. It occurs at the bottom part of the skateboard. Okay, the critical region is lying on the bottom of the wooden board, which contact with angle of wheel blade. So the highest region is represented by the red color in this figure. So it is about 19.98 megapascal. So it is mean that if the skateboard is going to fail, this region will fail first. So the next slide, it shows the result of simulation of displacement. So in this figure, we can see that the blue color represents the region where minimum deflection occur. And when it coming to the center of skateboard, the deflection is being increased and it reach the maximum deflection at the center of skateboard. So the maximum deflection is about 2.02 millimeter. For safety factor of skateboard in load case 1, it is about 1.001, which means that it is just reached the maximum load. So when a user with body weight more than 75 kg, it will cause failure of the skateboard. To prevent the failure of the skateboard, the user might step near to the fixture but not at the center of the skateboard. That's all from me. I will pass to my group member to present about load case 2. Thank you.
Hi, my name is Lin Chun Tek and I will be representing my group to present regarding the load case 2. So in our project, the load case 2 is chosen as the wheelie trick. So the wheelie trick is where the skateboarder he tries to balance the weight of his body on the skateboard, as you can see here. So this trick is performed by trying to lift the skateboard upward when pressing down at the back part of the skateboard. And at the same time, the user tries to balance the weight on this wheel. For this case, it is crucial to be investigated because we can see this trick performed at almost every skateboarding part, and this is actually quite dangerous trick depending on the board itself. We don't want the users to face any issues while doing this trick, especially if the board breaks. So this investigation is very crucial to determine if this board can actually support the user's weight by doing this wheelie trick. So in the simulation here, we can see that from this diagram we translated the weight of the person to the simulation, which is shown in the pink colored arrow. One at the back part of the skateboard and one at the front, the middle front part of the skateboard here. So for the purpose of our simulation, we assume the person using the skateboard to be 75 kg, and when translated into Newton, it is 735.75 Newton of load. And this load is to be distributed among these two regions here. And for the purpose of our simulation, we use the balsa wood and also the 7075-T6 aluminium for the bottom part of the skateboard, which we call it the truck. And this balsa wood is for the upper part of the skateboard, which is the board. To further explain for this case, I will be explaining for the parts of the skateboard so that we can understand it better. So there will be three major parts that we need to know. The first part is the board itself, which is here. The second part will be the truck. So the truck basically is the whole bottom part, including the assembly of the wheels. This is the 7075-T6 aluminium part, and also the bolt which connects the truck to the board. So when we run the simulation for Vollmeister stress, we found that there are three red regions. One at the place where the user steps on, which is at the lower end, one at the middle front, and another one at the bolt itself. So the highest region lies on the spot where the user steps on, and also on the bolt here, which is all shown in red colored. While for the other parts, there are almost no stress here, blue region, and in between we can see the green one, which is the region where it's close to the red region. Through the simulation, we found that the highest stress is 58.94 of megapascal, and this region lies in the bolt itself, which is at the back part. So for the displacement, we run the simulation and we found that the highest displacement occurs on the lower end of the board, which is this red region. This in a sense is true because the user tries to balance the board upward, and there is half of his weight distributed among this curved dimension of the board. So since it is curved, there will be a high deflection at that region. So this displacement here is found to be 1.876 of millimeters. While the front part where he steps, there is almost no deflection. It is very slow. It is very small, which is around the green and the cyan was 7.504 exponent to the negative 0.3 and also 5.628 exponent negative 0.3 of millimeters. Through this simulation, when we find for the safety factor, we found that the board actually fails. The safety factor that we obtained is 0.339, and when we calculate using the manual method by dividing the sigma yield by sigma von Mises, the sigma yield is 20. We got this from the online source and also the SolidWorks properties, which is 20 megapascal, and the sigma Vm, which is the sigma von Mises, we got it for 58.94, like just now for the maximum one. And when calculating it, we got 0.339. So in the solid mechanics theory, if the safety factor is less than 1, it actually fails. So this balsa wood is not recommended to be used for producing skateboard because it fails. So when the users try to do the wheelie trick, they might face issue where the board breaks, and they might eventually get injuries from there. So manufacturers should use maple wood instead to make the skateboard because it has a higher flexibility and also a better properties than the balsa wood. So for the critical load, as mentioned just now, it lies in the bolt of the skateboard, which connects the board and the track of the skateboard. It has a value of 58.94 megapascal. So yeah, that sums up for load case 2, and I will pass the rest to my friend.
So, thanks to Mr. Wekang and Lin Chung Teng for the great explanation for the load case 1 and the load case 2. So to conclude, we can make a comparison between these two load cases. The first thing is maximum stress at load case 2 is higher compared to the load case 1. It is expected since the weight of the skater at the load case 2 is distributed only on one side of wheel, while at the load case 2, the weight is distributed on two sides of wheel. Therefore, the load case 2 will have higher stress compared to the load case 1. However, based on our simulation, we find out that the maximum displacement at the load case 1 is higher compared to the maximum displacement at load case 2. Besides, the safety factor for the load case 1 is higher compared to the load case 2, where the value of the safety factor for the load case 2 is 0.339. It shows the skateboard will fail when the skater doing this trick. It shows that the deck, which is made of the balsa wood, cannot stand the impact force when doing this trick. So, higher properties of material is needed to avoid this failure. Based on the research, new material has been integrated to the deck, especially which are the fiberglass and Kevlar fiber. By integrating this material to the deck, the impact force can be distributed evenly, so the deck can last longer and can support higher load compared to the conventional deck. So, I think that's all from us, and thank you for your time.